Well, good morning, everybody. My name is Ari Pouttu. I'm a professor at the University of Oulu. My professor chair handles with dependable wireless communications for vertical applications. So applying wireless technologies into different business sectors of the society, maybe energy, industry, automotive, health, you name it, and there we try to find out what are the perfect solutions for each of these verticals, since their requirements tend to be very, very different. Secondly, I am the vice director of the 6G flagship program that we have running here at the University of Oulu. So I will tell you about the flagship today. We talk about a 6G flagship. Well, the Finnish government was rather forward-looking in 2017 when they launched the flagship program. And the flagship program coordination was handed over to Academy of Finland. And we submitted very late to 2017. All fields of sciences in Finland had an opportunity to submit a flagship proposal for Academy of Finland. And there were a huge number of those, if I remember correctly, close to 50 submissions. And Oulu University chose to submit a flagship on 6G topic. Now, many of you might ask why 6G, as we are very early stages in deploying 5G technology. We actually have only now the first release of 5G available, for instance, in Finland, where we are now enjoying the first capabilities of 5G. This release 15, as it is known, is mostly about what we call enhanced mobile broadband. So it's a step improvement for 4G, so providing faster data rates with a little bit lower delay, but still it's a mobile broadband continuation part of the 5G story. Now, why would we start doing a 6G now? Well, the reason is very simple. It takes about a decade to mature technologies, solutions, and algorithms to a level that standardization can then take place in the respective organizations who are doing the standardization. So it has been the same story already in 5G, 4G, 3G, that it should take about 10-year period to do research, development, and then standardization to come up with the standard for a cellular generation. So 10 years is a good time to start in advance. Now, what we have learned about the 6G is that, well, let's put it this way. In 2018, when we started this flagship program, 6G looked like an elephant that was being studied by a blind man. If he touches his tusk, the 6G seems to be very sharp. If he touches his trunk, then it's very wide, and the tail again is very narrow. So it seemed like an elephant, but like any big problem, also elephant is eaten part by part, and we were lucky enough to be the first in 6G, and therefore had an opportunity to really shape the 6G research agenda. Now, let's first discuss a little bit about what has happened over the years. Now, we all know that 1G, the NMT system, and 2G, the GSM, were basically offering voice services for human users. So it's all about the voice in the 1 and 2G era. Now, in the 3G and 4G era, the target was to put internet into our pockets. Still human-centric communications mostly. So mobile broadband into our pockets. And 3G started this journey, and 4G eventually brought the videos and all the services of the internet into our pockets. So now we are entering a 5G era, and the 5G promise is not in the enhanced mobile broadband only, but it's also in connecting objects, processes, services, and introducing native intelligence into the network to optimize the services and to optimize the network. Second thing that we have noticed, as you can see from these pictures of 1G, 2G, and so on and so forth, is that it seems that the market transformation, even though there is a new G every 10 years, the market transformation takes 20 years. And therefore, we have a strong expectation that similarly to earlier pairs of 1 and 2, 3 and 4Gs, 5G and 6G is a continuum that will transform the marketplace as well as introduce a major societal change so that this Internet of Things or Internet of Everything is going to take place in the next 20 years to come. What we believe is that this massive automation of society needs more than 5G can offer. 5G will definitely start the journey towards this Internet of Everything world. However, we already know now that 6G or 5G, beyond 5G technologies, will merge the physical and digital and biological worlds. And they will try to do it in a way where we try to fulfill the United Nations Sustainability Development Goals. Now, what does this actually mean? It means that we do have digital twin where we can control the physical world and can basically augment human senses so that it basically introduces a sixth sense for a human being, in a sense understanding what is happening around you using these new digital means. Now, a little bit about this Finnish 6G flagship program approach, and the vision for the flagship for 2030s is that the society will be data-driven, will be sustainable, and it is enabled by near-instant unlimited wireless connectivity. Our 6G flagship program is divided into 4 strategic research areas. The first area is the wireless connectivity solution. This particular research area is looking at technologies, algorithms, and ways how to transfer the bits that we are transmitting, the information that we are transmitting from our user device to the base station. So what are the technologies required to do this transfer of information from user device to base station? And the target values that we have set for this is to reach 1 terabit per second in the air, as well as extremely low latency, which means really fast reaction times, and up to 100 microsecond latencies over the air. This means that we can really do fast control, for instance. Second area of research is device and circuit technologies. Now, the problem with this 1 terabit per second data rates is that it starts to require huge amount of bandwidth, huge amount of spectrum. Easily it can need 50 gigahertz of spectrum, and these kind of chunks of spectrum are no longer available at the lower frequencies where the current cellular mobile systems are built. And therefore we need to go to higher frequency bands and beyond 100 gigahertz limit. Why do I say 100 gigahertz limit? Well, it seems to be that the current semiconductor materials widely used tend to fail in their capability to produce power for the transmissions when we go beyond 100 gigahertz, which means that we need to find new semiconductor materials that are efficient when we go to the higher frequencies. And secondly, this means that we need to figure out new ways to do the circuit designs when we have these new materials. And thirdly, these might entail some changes also into the manufacturing processes that are capable of then mass producing these new circuit technologies on new semiconductor materials. So these kind of research items are dealt with in this device and circuit technologies part. Third area is this distributed intelligent wireless computing. Now, we all are now used to these cloud computing services where in centralized clouds, a lot of computing happens, a lot of applications are running, and we just request, and computing request goes to this cloud computing facilities, may it be Google or Amazon or Microsoft or whatever. And then the answer is provided to us after a while. But the problem with this is that these servers are located in many cases far away from where the application actually is running itself. Even though radio signals travel close to the speed of light, the speed of light is slow. You might want to argue against that, but the fact is that we are looking on delays where we do transmission, computing, then transmit the information back to the application, and all of this should take only 1 millisecond or even half a millisecond. And that means that if we put a cloud computing center somewhere, let's say, for instance, in Helsinki, it takes easily 5 to 6 milliseconds just to transmit the information to Helsinki from Oulu and then back, and that's already too slow. So how do we introduce, first of all, computing into the network? So we need to have these edge computing servers around the network, close to the places where the computing is actually required. And second of all, we need to develop these intelligent computing algorithms that can provide, for instance, machine learning type of solutions or any artificial intelligence kind of functions that can support in optimizing either the network or the application programming or application computing that is being done. The fourth area, which is about services and applications, there we look at several things. One of them is, how do we consume data in the future? Currently, most of us have wireless device, smartphone, or a typical computer connected to the internet. This obviously will remain for unforeseeable time, but these will be complemented by new types of user equipment. They could be glasses with augmented reality capabilities, virtual reality capabilities. They could be holographic displays. So a lot of new ways to humans to interface with the data is going to appear, and that is one of the research areas that we are doing here. Second area is the vertical applications. How do we use the future technologies of wireless communications in, for instance, optimizing energy grids? Or how do we do the future 5G, 6G hospital augmented with artificial intelligence? Or how do we build the next generation entertainment in stadiums so that, for instance, a spectator can follow his favorite player and see the game from his eyes? So a lot of these kind of new applications in different vertical areas are appearing and will transform the way we see the world. Stemming from these 4 research areas, we have set 4 goals for the second phase of the flagship, which is starting in May this year. First of all, we want to provide still the detailed 6G technology enablers for all of these different research areas, so that we start to approach the capacity to do standardization with the companies that are working with us. Second goal is to build the world's first 6G test network. We currently have one of the most advanced 5G test networks in the world, where we can test services, applications, computing, test equipment, you name it. So basically we have a test network running at the University of Oulu where we can do a lot of testing, but it's still 5G and we want to transform it into 6G test network. Third area is this 6G vertical applications, as I mentioned before. When we start to have these 6G technology enablers, we need to figure out smart ways to introduce them into vertical applications. These machine type communications, for instance, so that, for instance, robots can talk to each other seamlessly in a fashion that it supports productivity, sustainability, and the business. And the fourth area, 6G vision leadership. We have been the first in 6G, and we wish to maintain this vision leadership and guide the world. Well, that's maybe too strong word, but give hints to the world where the 6G is going. We have impact actions also defined, and one of them is to really push this 6G enabled sustainable society. It was our invention to introduce these SDGs into 6G research agenda, and it's been adopted by European 6G flagship program, and it is one of the key outputs of this flagship program to introduce these UN SDGs as the driving force for some of the actions that is happening in the 6G research. We also have chosen 4 opportunity-rich vertical areas as strategic ones, where we do constantly try to find projects together with our partners to study how would we apply wireless communications, which is complemented with these native computing and AI solutions in health, industry, vehicular domain, as well as energy. But not limited to these, we do also other verticals. One of the key issues in standardizing anything is that we need to build global understanding, global consensus on the ways and on the approaches that we use when we develop a system. And hence we have this global 6G collaboration ongoing. We've had already for almost 2 years collaboration program with South Korea with their research institute, ETRI. Korea was the second in the world to provide their first 6G program. We have also a program with Japan. We are starting now to look at some aspects of 6G together with the Japanese. We are now having a 6G flagship program within the European Union, with the continuation being planned. Furthermore, we are discussing with the United States to start research most specifically in the spectrum domain and in these local private networking issues that we will deal with a little bit later in the talk. And also Germany and Singapore are being under discussion. And then the research infrastructure, as mentioned already, we want to be the world's first 6G enabled test networking operator. Now, the 6G flagship, as I mentioned, was the first in 6G, and we introduced several ways to provide view to 6G research globally. The first avenue of providing direction in 6G research was 6G Summit that we established in 2019. We organized it in Levi in 2019, and we're planning to organize it Levi in 2020, but COVID situation made us transform it into a online event. However, these summits were so successful that the European Union, now the Commission, and most, in particular, the DG Connect, the division on ICT, connected with us, and they wanted to organize their flagship conference called the EU CNC together with us with the 6G Summit program. And from 21 onwards until 24 at least, the conferences are now combined into a joint EU CNC and 6G Summit. And the next one will be held in Grenoble, France, 7 to 10 June in 2022. And most likely it's a online, it's a in-person event, but it will offer some online capabilities as well. The second avenue of dissemination of our ideas, what the 6G research agenda should look like, are the 12 white papers we have provided. These white papers are not just about technology, they represent also the 6G, what the business landscape could look like, how do we deal with the sustainability in 6G era, and what are the regulatory barriers, requirements for 6G to be widely adopted through different verticals and in different areas. And obviously, the technology itself. What are the solutions that we currently foresee for these 6G system solutions? And furthermore, we have this webinar series as well as an easy to read 6G Waves magazine, which we typically release every 6 months. Now, what is different in 6G compared to 5G? 5G is still a system, currently at least, a system offering communication services. It will start the journey to be computing native with AI solutions. However, when we go high in the frequency domain, in 6G era, we start to see new capabilities appearing with these higher frequencies and the new array antennas that need to be introduced with 6G devices. And these array antennas and higher spectrum will allow us to use the same communication signal that we now transfer bits with, also to sense the environment, even image the environment, and get a highly accurate positioning capability down to millimeter level. And this obviously opens huge number of opportunities for any applications you might think. Now, let's discuss a little bit about what kind of key performance indicators there might be for 6G and what they might mean in terms of capabilities. This is not an exhaustive list. This is just like an example of what these different requirements might mean. If we take a look at the table and take first look at the upper right corner of the boxes, it says 1 terabit per second. So what does this kind of data rate basically make possible? First of all, there is new ways of consuming data, namely the holography. This is a very interesting topic, and we shall try to, in the next couple of years, come up with some kind of wireless holography services in national, but mostly in Horizon Europe level projects. Second of all, it will allow for a very accurate extended reality world. You can, if you think about 16K resolution with 240 Hertz refresh rate, 360-degree digital twins, you can easily understand that the data rates required to maintain such an environment is huge, and obviously the experience would be almost real life-like. We can also start thinking about in-chip radio. So inside your user devices, instead of having these leads, you start to have radios inside your devices. In-device radio, and for instance, data center connectivity, getting away from the cabling in different data centers. Data kiosks. Many of us have been driving a car along the highway, and then there is somebody in the back seat saying, "Daddy, when are we there?" And if you have opportunity in 1 second download while you're driving something that is entertaining for the kids, it might help you to, let's say, make the journey more enjoyable. Now, huge data sets, for instance, human DNA, mapping of the DNA with almost real-time devices, astronomy. Astronomers, for instance, in these huge arrays produce terabits per data per day. So it's something that could be benefiting from these. When we take a look at the upper left-hand corner, we can see there's 100 microseconds, which means the latency. How fast can we transmit? And this basically gives us an opportunity to have remote control with haptics in a hysteresis-free fashion. Haptics basically means that you can do remote control as if you were in the place. So you can feel in your hands what is happening at the receiving end, where whatever is being done, whether it's excavator being remote controlled, or whether it's a surgical instrument that you are wielding on a patient, and you should have some kind of a feel so that you know what's happening there. Second example comes from the energy domain, active protection circuitry. One of the big issues and costly issues is the fuses in electrical grids. When they break or when they pop out, you always, well, almost always need to send a human being to take care of the problem, and that is rather expensive. People are talking about active protection circuitries, and this might be require really low latencies, not to burn, for instance, substations. And if we talk about industrial process control, people are nowadays talking about 200 Hertz control loops, meaning that from the transmit, for instance, a robot requests something, you have 500 microseconds to send the request, do the computing, resend it back to the robot. So you have 100 microsecond on the air, 100 going back, and then you have 250 microseconds for processing the request at the edge server, and 50 microseconds to implement whatever was computed. So therefore, we really start to see the need for these low latency communications. for instance, in LTE, the minimum the latency or transmit delay based on the signaling structure is 10 milliseconds. And now we talk about 1,000 times faster latencies or lower latencies compared to, for instance, with the LTE. On the lower left-hand corner, you can see 10 nanoseconds. This means that in some industrial applications, and for instance, in holography, you need to have jitter-free transmissions. You need to always get the signal at the same time. Even though that it might be that the latency is not anymore so important, but it has to arrive always at the same time. And for instance, if you have multi-stream holography, you need to synchronize the streams very accurately so that you can get good holographies out of it. Industrial Ethernet is another thing. In some industrial applications, you may need in the future really low jitter so that you can really push these applications, control applications to the limit. And then there is this 1 to 3 millimeter box on the lower right-hand corner. And this means the sensing and imaging accuracy and the location accuracy. Now, what do these low millimeter level values offer us? It can offer us, again, help in holography, but also in these real-time digital twins and virtual remote control applications. If you can, using the same communication signals, map your environment to come up with real-time digital twins, and you can then also build the virtual remote control into these digital twins, then you have close real-time operation system that you can run in a virtual fashion. For instance, from the convenience of your home, you can use, for instance, a excavator from your sofa. Extreme swarms, for instance, drones. Sometimes that could be a good application. Material identification, for instance, in process control, to see what type of products or material flows are there problems, so on and so forth. All these complemented these communication capabilities, sensing and imaging capabilities, complemented with AI solutions, allows us to see the future, at least a little bit into the future. Let's, for instance, talk about driving a car or self-driving cars. We know that from around the corner there are cars coming because we have the communications, and the AI is computing the solutions which prevent, for instance, accidents. So we can see into the future, around the corner, what's happening in the next few seconds. So the augmented human with seeing the future capability is something that could be one of the outcomes of the native AI with 6G capabilities. So this is not a, let's say, activity by our university of alone. This 6G Flagship is a multidisciplinary research roadmap with multi-stakeholder collaboration. We have several academic partners, research institutes. We have industry partners and public sector partners, regulatory partners, for instance. Currently, the 6G Flagship ecosystem contains close to 1,000 organizations, of which 300 are companies, close to 600 academia, close to 100 are public sector actors. And out of these 300 industry companies, close to 150 are participating in research projects in either in funding or receiving funding in a collaborative action. We, as I mentioned already earlier, the UN SDGs were introduced by the 6G Flagship as the global driver for the 6G R&D. And we have been very strong in contributing to the ITUR, which is in the next couple of years providing the requirements for 6G system. And that is something that we really want to push as part of the vision leadership goal in our program. One more slide about these experimental capabilities. We started building a test network for 5G solutions in 2015. Eventually, a couple of years ago, 3 years ago, we had the 5G enabled capabilities. And we also became a what we call micro operator. So we basically have our SIM cards, which we can hand out to any customer who wants to do, for mobile application testing, or introduce narrowband IoT modems into the network and test how these new designs work, or whatever. So we are now basically operator grade 5G micro operator network. We have also had success in terms of acquiring, let's say, funding for maintaining this infrastructure. Namely, Academy of Finland has selected this together with VTT, Aalto and Tampere as part of the Finnish research infrastructure roadmap, and that enables us to buy the next generation equipment when we go further and further into the 5G and beyond 5G domain, as well as eventually to the 6G domain. We have also been selected as part of a 15 European country and 30 partner project proposal as part of the European research infrastructure roadmap, which again will give us European level visibility in terms of offering these services to European level players. What we expect to see is first 6G proof of concept devices maybe in 2023. Why? Well, those will be very simple, very not very capable, but anyways, first 6G proof of concept devices are expected late 23, and the first 6G in quotes network in 25, so that we have few of these 6G devices connected to the network infrastructure, and therefore being able to do tests on real 6G technologies. And the 6G standardization will begin in 2026. That is the current estimation. And we expect to see 6G technologies entering the market somewhere in 2030. Now, I've been talking about this high-end 6G for most of the time, but that is not the only path that is happening. It's for researcher definitely the most interesting part. And in the lower hand corner or right hand corner, you can see 3 paths towards 6G. So the disruptive 6G path was the one that I've been mostly discussing about in this presentation. But there will also be this 3GPP, which is standardization organization for mobile cellular systems. And they provide a new release of a standard, give or take, every 18 months. And now we have release 16 available, which is the next step in 5G domain. And we believe we can acquire those devices soonish, probably during summertime first, the release 16 devices, which already provide these ultra reliable, low latency capabilities of the 5G, which means that they will offer us the capabilities for this machine type communications. And then there will be release 17 available a couple of years after that, which means that the third corner of this 5G, namely these massive machine type communication capabilities with reduced capabilities devices, so using less energy and really targeting the IoT market, will be available maybe in 24. The third path is what we call open source or open RAN path. In this particular path, we expect to see general purpose devices transformed into for instance, cellular base station. Basically what it means that you can download onto a powerful computer software and then connect it with a software-defined radio. You can use this as a base station. It is applicable to some applications, not every applications, but it could be usable for certain things in this 6G era. So we are trying to cover all of these three paths to deliver services to our collaborators and partners. Why then bother with the experimental test networks? One answer to this question is the versatility of vertical requirements. In one of the white papers, we discuss how does it look from different vertical perspectives, the requirements for different KPIs. For instance, latency. Latency is very important, for instance, in mobility or industrial critical communication. But then again, it's not so critical, for instance, for finance or this massive type communication, for instance, environmental sensors or things like that. Then if you talk about density, for instance, how many devices per cubic meter or square meter you would have, you can easily see that in mobility, for instance, in cars, you might easily have 100 radios per square cubic meter, basically replacing the wires with radios in a car. But then on the other hand, if you have agribusiness, you might have 100 radios per square kilometer. So these different requirements and testing the capabilities in different verticals require a very flexible test networks to be able to try out and develop the solutions applications for different verticals. And one of the reasons, another reason is that the technologies start to be so complex that it's sometimes difficult to get really reliable results only using simulations or analytic approaches in assessing the performance of a system, and therefore experimental test networks are needed. Well, one more slide about the planned radio park in Oulu, Finland. So there is an exercise ongoing where we are trying to build a facility which would then offer wide range of development, measurement, and experimentation tools for the next generation wireless systems, including, for instance, indoor over-the-air RF testing, how to integrate software and hardware facilities and outdoor test areas. For instance, Oulu zone where you can try out heavy machinery or drones, also different environmental labs and so on and so forth. And obviously also some design facilities, research facilities. So I believe I have consumed my time and to leave something for the questions, if there are any. Just want to let you know where you can find these white papers. If you are interested in any of or all of these topics, you can find them from the address 6gchannel.com/6g white papers. So with this, I believe I have used my time and I conclude my presentation. Thank you very much.
Thank you very much, Ari. There are a few questions. Can you see them in the Q&A section, or do I read them to you?
I cannot see the queue. Oh, published. There you go.
Yes. There's
Okay.
2 questions and to my.
Yeah. What is the security of Internet of Everything? It's a question from Ari. That is a most definitely a very important question. And we all know that when we go towards multi-stakeholder networks that we probably will start to see in 6G era with the introduction of more open APIs into the system so that many players can develop computing algorithms and solutions for the networking and so on and so forth, the number of the threat vectors will basically explode. And personally, I'm not a security person, but there is a white paper on security, trust, and privacy in 6G, which is at least partially touching this topic. But this is definitely sort of like a security by design kind of question. Wildest ideas have been so that any device to be connected into the next generation networks would be having a hardware coded ID which is associated with any IP that you might have, so that if there is any malware or bad actions, these kind of devices would be basically shut down. Take a look at the white paper and you might have some answers for this question. Then there is a question on how far can we go regarding speed and latency? When will we face the limits? And will the usage area be limited to centimeters at some point when the frequency gets higher? Well, this is an interesting asymptotic question. It's all about, obviously, it's all about, speed of light. If we talk about 100 microseconds, that basically is 30 kilometers. It cannot be that long. So if we talk about 100 microseconds, you typically talk about few kilometers. It will be limited to centimeters when you go to nanosecond latency level. I mean, 1 nanosecond is 30 centimeters. And but that's most likely not the solution that is available until maybe 9G. So we talk about less than 10 kilometers if we talk about 100 microsecond latencies. In terms of the data rates, 1 terabit per second will obviously be already a huge challenge in the next 10 years. It might take 20 years to reach to 1 terabit per second. People are talking about somewhere between 100 giga and 1 terabit per second for 2030s. It depends on the development on the semiconductor materials. I believe that's the biggest hindrance at the moment that we see. Then there is a question. China is not a partner country. Is because of A, language barrier, B, geolocation meaning distance, C, US-China hostility in business, D, US-China hostility in politics, E, Europe-US global strategy, something else. Let me put it this way. It's C, D, and E. And why? Well, we have a lot of European partners and we have some US partners in this program. And the Finnish security police as well as ministries have educated us to be very careful with that currently with the Chinese partners. Hence, China is not currently, or Chinese companies are not currently part of the ecosystem. There are a few Chinese universities whom we do purely academic work, not any project work. Money is not changing hands, but researchers do have their networks, but no research with Chinese partners that is seen to be in any fashion controversial. Then there is Janne asking a question, Janne Mustonen, about the business opportunities for micro operators and private networks. This is definitely one of the ways to go. The micro operator is typically a player who can build networks and specifically for a vertical. Let's think about, for instance, a micro operator who specializes in stadium services. He really optimizes his product portfolio to be able to provide services for ice hockey halls or big football stadiums. And he's the expert. He knows exactly what to do, how to run the show, how to build it. But the guy who owns the premises will become the king in this game. He's in the driving seat. He chooses who will build his network. And if his business is, for instance, sports and stadiums, if there is a player, micro operator, vertical service provider who can provide optimized solutions, he most likely would like to do that rather than going for a national mobile network operator who is excellent in providing nationwide coverage. Obviously, some of these micro operation business opportunities could be adopted by mobile network operators, definitely so, but that depends on the mobile network operator, whether they adopt this model and start offering it to any vertical players in the market. And that is going to be the big change. And we have already started to see that. I know already, for instance, that Nokia has more than 400, close to 500 private networks that they are running for their customers. So definitely these micro-operated vertical specific service provider networks will become one of the complementary solutions in the future cellular market. Then there is just a practical question about 16K at 24 Hertz, means 30 gigapixels per second. Do you predict it will be feasible? Not soon. It could be somewhere in 2030s, might not even be in early 2030s, could be somewhere in mid 2030s, I would expect. I haven't done any calculation if we think about this Morse law and how fast the capabilities develop. You probably could get some kind of an estimation of how fast we will get there, but really haven't done any calculus on this one. I believe it will be feasible. Obviously, locally, I mean, for instance, you can have an application running at home or application running at, for instance, in an industrial factory, but obviously not a global solution anyways. Then there's a question about, do you see that principle of transfer will be changed so that we start to transfer more information instead of data in the 6G? There is this metadata kind of thinking in Shannon's famous paper where using other domains than just bits would reach higher capabilities for transferring information. Definitely so. The research has started a couple of years ago on these principles, and whether it's already available in the early stages of 6G, I do not have an answer for that. Might be. But the research is there, and if it proves to be feasible, then it might already be one of the topics to be introduced in 6G. I guess that concludes the questions, and I hope I answered the people with satisfactory fashion, and I also think that we are about in the end of the session, I believe.
Yes, thank you very much, Ari. Great presentations and some nice comments and good answers, and thank you for the participants who